All right, let's dive right into this explainer and look at how the math has recently shifted away from traditional fission toward the absolute utopian promise of fusion energy. For years, fission was basically deemed a pipe dream. It was considered way too expensive, burdened with massive regulatory hurdles, and starved of raw materials. Honestly, it just made more sense to aggressively fund traditional fission reactors instead. But the math and the technology are shifting right before our eyes. So today, we're going to unpack the real roadblocks to limitless clean energy. To kick off our cinematic journey here, we have to ask a pretty massive question. If small atoms naturally want to fuse into more stable configurations, like helium, why isn't fusion powering our grid today? Fission, as you might know, happens in large, unwieldy atoms that are desperately trying to move toward stability. Well, fusion is the exact opposite. In this subatomic energy economy, small atoms undergo fusion to reach a more stable configuration. And Helium is the absolute star of this show. It possesses an incredibly high binding energy. You can think of binding energy as the ultimate state of subatomic relaxation. Elements below helium find it highly favorable to fuse and reach that perfectly relaxed state. So, if it's so favorable, why don't we see fusion happening around us all the time? Section 1. The Fusion Paradigm Shift. To truly grasp what startups like Commonwealth Fusion Systems are attempting with their new Spark reactor, we need to picture a stunning, microscopic battlefield. At the micro level, atomic nuclei naturally repel each other. This is due to the electromagnetic force. That invisible shield absolutely dominates at slightly larger scales, keeping those positively charged nuclei far apart. But if you can somehow get them close enough, the strong nuclear force takes over. And that force is unbelievably powerful, but it only acts over incredibly minuscule distances. This means we literally have to pump massive amounts of energy into the system just to force them close enough for that strong nuclear force to kick in, overpower the repulsion, and snap them together into a stable configuration. Section 2. The subatomic collision. So, when those atoms finally do collide and that strong nuclear force wins the battle, something incredible happens. The reaction releases a highly energetic neutron. That tiny, incredibly fast particle is our ultimate prize, because it carries the energy we want to capture. Basically, we have 3 distinct hurdles to overcome to make this whole thing a reality. First, get the deuterium and tritium fuel. Second, get them close enough to overcome that electromagnetic force. And third, extract the energy from that speedy neutron to turn it into electricity, which we usually do by boiling water. We're actually going to look at step 2 first, because the visual engineering behind it is just absolutely fascinating. Section 3. The magnetic breakthrough. Zooming out to the macro scale, the Spark reactor uses this brilliant donut-shaped machine called a tokamak. It ionizes gas into a superheated plasma and pumps energy into the system using radio waves to generate massive, literally sun-like heat. But obviously, you can't just let violently hot plasma touch the physical walls of your machine. It would melt instantly. Instead, they keep that plasma perfectly shaped and safely suspended in a vacuum using immensely powerful REBCO magnets. And guys, these aren't your average refrigerator magnets. We are talking about crafting invisible magnetic cages so unbelievably strong that they could literally lift an aircraft carrier. They squeeze and shape the glowing plasma into an optimized configuration just to maximize the probability of fusion actually occurring. But remember that highly energetic neutron, our grand prize? Well, neutrons don't have an electrical charge. That means they completely ignore those massive magnetic cages we just built. They fly in a perfectly straight line from exactly where they were created and crash directly into the reactor's inner wall and neutron shield. To efficiently extract their immense heat, we use a concept exactly like playing pool. Think of billiard balls. If a billiard ball hits something much heavier, it just bounces off. But if it hits another ball of a similar mass, it transfers almost all of its kinetic energy. So we crash these newly born neutrons into a shield made of small atomic nuclei of similar mass, which maximizes the energy transfer. Now, to put this into perspective, let's compare Spark to the massive 30-year international ITR project. The physical contrast here is just striking. ITR is a colossal undertaking. It's designed to produce 500 megawatts of fusion heat in a giant 830 cubic meter plasma chamber backed by 35 nations. Spark, on the other hand, aims for 140 megawatts in a much tighter, incredibly compact machine. In fact, MIT has described Spark as being roughly 12 times more power dense than ITR. It's a lean, highly efficient machine attempting to prove the fundamental reactor tech is sound and doing it on a much faster timeline. So the reactor works. But that brings us to the next massive challenge. Section 4. The Great Tritium Drought. Right as we solve the magnetic confinement and the energy extraction, we hit a highly dramatic complication: finding the actual fuel. Deuterium is common enough. About 0.016% of natural water contains at least one deuterium atom, so we are perfectly fine there. But tritium? That is an entirely different story. Through its heavy water CANDU fission reactors, Canada provides most of the world's commercial tritium. Heavy water is used as a moderator and coolant in those reactors, and when it's subjected to neutron flux, it creates tritiated heavy water. From this entire process, we extract a grand total of just 2 kilograms of tritium per year globally. Just 2 kilograms. Why is that 2 kilograms such a massive problem? Well, because a single gigawatt-scale fusion power plant needs roughly 55 kilograms of tritium every single year just to operate. That means the entire global supply chain, which is heavily reliant on Canada's annual output, could barely run one enthusiastic neighborhood. You know, maybe one with heated driveways and 6 waffle makers in every house. It is absolutely nowhere near enough to power a global grid. And to make matters exponentially worse, the current civilian stockpile is sitting at a mere 20 to 30 kilograms total. And because tritium has a half-life of just 12 years, that stockpile is constantly fading away. Roughly 5.5% of it simply vanishes to decay every single year. We are in a literal race against physics just to keep the fuel we already possess. Section 5. Breeding fuel from blankets. So how on earth do we solve this vanishing bottleneck? The whole point of fusion is clean energy, right? It makes absolutely no sense to build redundant, traditional fission plants all over the world just to harvest the fuel needed for fusion. We need a better way. Nature, thankfully, offers a pretty fascinating loophole. If we wrap the tokamak reactor in a warm, cozy blanket of lithium-6, magic happens. When that energetic neutron created during fusion flies out and hits the lithium blanket, it splits the lithium into helium and tritium. Through this transmutation, literally splitting and transforming the element, the reactor theoretically breeds its very own fuel right on site. And, as an added bonus, this generates a decent chunk of extra heat in the blanket, which we can then use to spin turbines and generate even more electricity. Section 6. The reality of timelines. Now, let's look at the sobering reality of all this. The giant asterisk on this whole operation is that this cozy lithium-6 blanket, it doesn't exist yet. It's not on Spark, it's not on ITER. In fact, ITER is only planning to test 4 small mock-up designs which together might produce just 1% of ITER's own tritium consumption. The technology to breed the fuel is entirely theoretical at a commercial scale right now. When we compare the upcoming reactors, we can clearly see the stepping stones. The Spark reactor, which is scheduled for first plasma in 2027, is really just a demonstration. It will only fire in 10-second bursts. Now, that's long enough to prove the physics of getting more energy out than we put in, but crucially, it has no breeding blanket. The follow-up, the ARC reactor planned for the early 2030s, is the one actually aiming for the grid. ARC plans to use a Fleabee molten salt blanket, which is a mix of lithium fluoride and beryllium salt based on 1960s fission heritage, to finally breed its own fuel. Looking at our timeline, you can see how this all builds together. In 2027, Spark proves the physics. But we won't truly know if the commercial reactor can reliably breed its own fuel until the ARC reactor fires up around the early 2030s. Given the pace of progress and, sure, potential boosts from AI breakthroughs, we are looking at a roadmap where the broader energy landscape might not fully transform until 2060. This is exactly what you should take away from this. The clean energy revolution we constantly hear about is still a multi-decade marathon, not a sprint. So the ultimate question we are left with is this. The subatomic physics of fusion are finally within our grasp, and the magnetic cages work beautifully, but can we engineer and scale the massive, unproven lithium supply chains and breeding blankets needed to sustain it before the world's patience and our incredibly precious tritium supply simply decays away?